So this is the free response problem number 2 from 2015. So I'll give you a moment to look over it. So you may want to pause the video so you can read the problem. Okay, so here's problem number 2. They give you these two functions and they give you a graph of these two functions. F of x, which is right here. Since you're on the calculator part, you can actually verify this, but f of x is this function. And g of x, whose equation is right here, is this function. So when we go to set this up, you know which graph is which. And part A says, well, I've got these two regions, R and S. R is this region, S is this region. They label everything clearly in the picture for you. So part A says find the sum of the regions of R, sum of the areas of the regions of R and S. So if you look at region R, which is this one, that's the area between two functions. And that function that's on top is g of x. The function that's on bottom is f of x. And if you look at this region, region S, the functions switch places. So when we set up these integrals, you're going to have one function on top and one integral, meaning coming first before the subtraction, and flip the order of the second integral. So the one thing we need in order to actually set this thing up is the transition spot, the place where those two graphs intersect. So what I did is I graphed these things on my calculator and used the intersect function on my calculator to find that number. And that number was 1.0328-ish. I'm going to label that, the crossing point there, as 1.0328-ish. But when I go to do my work, I'm going to label that with a letter. Let's call it B. If you label that with a letter in your work, you can actually use that letter B throughout the course of the problem instead of having to rewrite the decimal over and over again. It's the same sort of idea as storing the number in the calculator. So for part A, the sum of these two regions. In region R, g of x is on top. So the integrand there would be g of x minus f of x with respect to x. We start this area at 0, and we end this area at b. So I'm going to put a b here, and since I've already defined what b is, I don't have to rewrite that variable. And then, when I go to the second integral, this will be the integral starting at b and going to 2, and the two functions will switch places because the one that's on top has changed spots. So I would use my calculator to calculate this, probably by doing the integral of g of x and f of x separately and writing those things down as separate and subtracting them and doing the same thing here and adding them, subtracting those, and then adding those two things together. Just make sure when you write those numbers down that you actually get more than just the 3 decimal places on each of these individual numbers, just so you can get the numbers correct. So I did that on my calculator, and I got that this comes out to be 2.0043. So 2.004, and that's the answer to part A. So part B says that region S is the base of a solid with cross-sections perpendicular to the x-axis. So this is a slicing method. So whenever we're doing slicing, it says perpendicular to the x-axis. So that means it's a dx integral. And whenever you're doing a volume by slicing, the volume is the definite integral from a to b of a of x, d of x, where a of x is that cross-sectional area in terms of x. That's what it is if it's perpendicular to the x. If it's perpendicular to the y, it's a of y dy, right? So I'm going to draw a picture of the cross-section, which in this case is a square. So you know how to find the area of a square. Area of a square is side squared, right? So we just need the length of the side. Well, it says the base of the square is in the region S when you cut perpendicular to the x-axis. So this line segment right here is right here in the picture, in region S, in the region perpendicular to the x-axis. So you see these endpoints are attached to the two functions, and if I slid it around in S, the length would change, and that length would be dependent on the vertical distance between the top and bottom function. So in that area, the top function was f of x, and the bottom function was g of x. So this length is f of x minus g of x, which means this cross-sectional area in terms of x would be f of x minus g of x quantity squared. So when I go to the volume now, the volume of this thing, the integrand, would be f of x minus g of x quantity squared with respect to x. And now all I need are my starting and ending points. But those would be the same as it was in the area of that region. It would start at the intersection point, which we labeled B, and would end at the other intersection point, which is 2. So now I would take this and actually find the integral using my calculator. And I did that already, and I got 1.1696. I don't like rounding where I have to change several decimal points, so I'm just going to leave the extra decimal point on there. So that's part B. Part C says, find the vertical distance between the graphs of f and g in region S. So vertical distance, remember, this is part C, not part B, is top minus bottom. So the vertical distance, which is h, is between graphs f and g in region S. So remember at S, f of x is on top. So f of x minus g of x is what h is. And then it says find the rate of change at which h changes with respect to x when x equals 1.8. So really what I want is h prime of 1.8. Well, when you find the derivative of things that are subtracted, you do those separately. So h prime would be f prime minus g prime, and then when I plug in 1.8 into each of those, that would give me the actual value of the rate of change at that point. So I've done that on my calculator. It's negative 3.8117. So negative 3.812. So that would be the answer to part C. And that's the entirety of number 2.